Well, this would be our final precept, precept 11. We're going to talk about the substring search, and KMP we'll think about the non-deterministic finite automata and the Boyer-Moore algorithm for string comparison. So we'll start with the first problem, which is to given a string, we want to build a machine, a DFA. We want to build a DFA to recognize the string. So the way we do that is to think about as the text input go through this machine, the machine will go from one state to another state. It will transition. And then finally gets to the final state, we will say we will accept the string. So how do we think about this? I think the first one is very, very easy. If you're in state 0, the initial state, if you see an A, you go to state 1. If you're in 1, you see a B, you go to state 2. And same way we can write down all the transition states. And then finally we get the final A here. It's going to go to state 6. So transition states are easy. So 1 here, B, you go to 2, 3, see another, you go to 4. When you're in 4, you see a B, you go to 5. When you're in 5, you see an A, you go to 6. So the question is now, what are the non-transition states? So what are these things? So for instance, if you see a B when you're in state 0, you're going to stay in state 0. Because there's no place you can go. You can only transition when you see an A. So this means that this would be a 0. Now, suppose you're in state 1 and you see an A. If you see an A, we know that we have seen an A before. The reason you're in state 1 is because you have seen an A. So if you see another A, you can just stay there because this means that you have seen an A. So just stay there. So this means this would be, we would stay in state 1. And then if you're in state 2, this means that you have seen the string AB. That's why you're in state 2. And then you see, if you see another B, think about what's going to happen. If you see another B, now this is where we have to be careful. So if you're in state 2, you have seen AB. You see another B, now you have seen ABB. Now, we want to know where to back up. Now, to determine that, the way I recommend that you do this is to think about the longest suffix. So these are the suffixes of the string ABB. Longest suffix, which is also a prefix. In this case, it happens to be empty string. So therefore, if this happens, you should go back to the state 0. So this is going to be 0. Now let's think about this case here. If you're in state 3, this means that you have seen ABA and ABA, and now you see another B. So the question is, what's going to happen? So we think about the longest suffix, which is also a prefix. In this case, it's AB. This means that if you see a B, you can go back to state where AB is recognized, which is the state 2. So you can return here. So now we look at state 4. State 4 means that you have seen AB, AA. And when you see an A, we want to determine where do we want to return. So we have ABA plus we see an A now. So look for the longest suffix, which is also a prefix. It turns out that A is the longest suffix. That's also a prefix. So therefore, you're going to go to 1 here. So if you see an A, you're going to return to state 1. So now, when you're here, let's see what happens if you see a B. This means that you have seen AB, AA, B. If you see a B, this means you have AB, AA, B. And then you have seen another B. Now we want to know the longest suffix, which is also a prefix. Unfortunately, there's no longest suffix, which is a prefix. It's the empty string. So you're going to go back to state 0. So this means this is state 0. So if you take a string and if any text string runs through this machine, if that text string contains AB, AA, BA, it's going to get to the accept state. So this is shows you how the KMP table can be built given the string, and we can figure out exactly what the tables can look like. So here's another type of a problem. This is very interesting, but it can be very tricky. So we have to be careful in determining how to find it. It says it's a partially completed KMP DFA for some string S. We have no idea what the string S is over the alphabet AB. We want to know what the DFA as and what the S is. So there are a few clues that we can get immediately from this. For instance, the transition states indicate that we know the character at that place. If you're in state 2, you see a B, you go into 3, so this means that character must be B. The same thing here. This must be an A. This must be an A. So we know that those things can be determined. We can use these to figure out what the transition states are. So those are the BAA. And the other thing we know is that at least one of them must be transitioning a transition state. So you have to go forward. So this means that we know this has to be 1, so hence this character has to be B. And because this is 1 and one of them must be transitioning to the next state, this must be 2, hence this character must be A. Let's think about the other things that we know of. So we know that in this case, if you're in state 6, you're going to be going to state 5. And if you see a B, if you're in state 6, you're going to be going to state 5. So what that means is that just before you got to state 6, you have seen an A, and now you see a B, and this means that you're jumping back to this state here. So I'm going to claim that these two characters are A and B, because those two characters are the same as what happened here. All right, one more time. By the time you came to the state 6, the last thing you saw was an A. In state 6, you saw a B. That means you have seen AB, and it wants you to jump back to 5. This means the two characters that you saw just before that must be AB. So we solved that problem. Now, so let's try to solve the other problems. The other problems we want to solve. Question is that one of these is a transition state. So therefore, this has to be 7 because this is going back to 5. One of them must transition. Hence, this character must be A. So now I think we figured out what the string is. It's BAB, AB, AAA. Now we should be able to fill out the rest of the table. So to figure out what this is, again, we can follow the methods we used before. This means that you have seen a BA. That's why you're in state 2. If you see another A, look for the longest suffix that's also a prefix. So we know that's 0, because if you're in state 2 and you see another A, that's a string you have seen. The longest suffix that's a prefix is a 0. Now, if you're in state 3, we know that this has to be 4 because it's advancing. This has to be 5. That's advancing. Now the question is, what is this here? So this means that you have seen BAB, then now you see a B. So we are looking for the longest suffix, which is a prefix. So if you take BAB and you see another B, what's the longest suffix, which is a prefix? It's going to be the 1. So this means that's the state where you have seen a B. So in this case, we have seen BA, BA. Now we see another A. what's the longest suffix that is a prefix. It turns out that BA, then we see another A, the longest suffix that's a prefix is empty. So this means that this must go back to 0. Now in here we have seen BAB, AB, we see another B, so we have BAB, AB, and you see another B. So what's the longest suffix that's a prefix? It turns out that it's a B, and hence this must be 1. In this case, we have seen BAB, AB, AA. We see another B. So where do we return? We see another B. What's the longest suffix that's a prefix? That's going to be a B. So therefore, we return to 1. So hence, we completed the KMP table based on the partial information. All right, so this is a problem where we would try to build an NFA to recognize any regular expressions. You can read the lecture slides to see that given regular expressions, there's a DFA. Given a DFA, there's a regular expression, but because DFAs can have infinitely many states, we don't want to do that. We represent a regular expression by an NFA. So to build this NFA, to construct this, what we need to do is follow some of the rules. The rules are the add match transition edge from state. When a character matches, add a match transition. That's going to be a black edge. You can think of, if you really implement this, this is like a directed graph with a bunch of vertices and edges. Epsilon transitions. Let's add some epsilon transitions from parentheses to next state. So let's go from parentheses to next state. These are the epsilon transitions from parentheses to next states. The next, we have 3 epsilon transitions from each of the star operators. So this is the easiest one. I'm going to go this way, this way, this way. Star means that you can have 0 or more. These are the things corresponding to the star operators. There's another star thing here. To deal with this, we need to have 1 going forward. We need to have 3 of them. Because it's around the parentheses, we should return back here and then back here. So we have 3 epsilon transitions corresponding to that star operator. So we take care of that. And then finally, we want to do epsilon transitions for the O operator. For that, I'm going to use a different color just to make things a little bit more clear. So one of them is that if you're here, if you do not use this, you will jump here, and this is an epsilon transition corresponding to the O operator. And if you decide to take this route and took this, you must jump all the way back to the final parentheses. So this means if you choose A, you cannot choose any of the other expressions. The second one is this one here. So this means that if you decide to skip this completely, then you would be going from this state to the state here. And if you decide to take this route, then you must go skip and go to here. So this is the next one for that. So those are the 2 epsilon transitions that you can take as a result of having the O operator. So this completes the machine. It's a directed graph, and it can be implemented as such if you really want to implement this NFA. All right, so that concludes that part of the. So the next problem is based on the NFA simulation. what we're trying to determine is that given an NFA, as this, the machine, and given a string, we want to know whether the string is going to be accepted, and how do we know that? This means that if you run the string through the NFA, you must reach the accept state. Now, unlike a DFA, NFA can be in multiple states at any given point. So for instance, even if you don't read any characters, you can be in state 0, or you can take epsilon transitions to 1, 2, 3, 4, or if you're in 1, you can take a transition to 6. So even before you read any characters, you can be in state 0, 1, 2, 3, 4, 6. Now suppose we read a character. So after you read a character, if you're in state 2, you can go to state 3, you can come back to 2. This means that after you read A, you can be in 2 or 3 or 4 for sure. And also, because you were in 6 before, you can be now in 7. Because you read an A and that match, and that takes you to 7. So those are the states that you can be in after reading the empty character and the A. Suppose you read another A. Let's see what happens. From where can we go from these states? So the machine is in these states, and where can the machine transition to? So if you read another A, and if you're in 2, you can go to 3, come back to 2. So therefore 2, 3, and 4 are still there. And if you read another A, if you're in 7, there's nothing you can do and nothing happens. So you're not going to go to any other state. So you would be in 2, 3, 4. So after reading the third character, again, you would be in 2, 3, 4. Nothing else happened, and you're stuck in this loop here. So the next you read the character B. If you're in 2, 3, 4, especially if you're in 4, I can go to 5. So now we can go to 5. And once you go to 5, you can go to 8. Once you go to 8, you can go to 9. And you're stuck. There's nothing more you can do. Now, and we ran out of characters. Therefore, we never reach the accept state. And therefore, we say that string will not be accepted by this machine. Let's take a look at another one. So this is the same problem, same as before, without reading any characters. It can mean state 0, 1, 2, 3, 4, and 6. And once you read A, so if you read the character A, you can go to 3, and you can go to 2, back to 2, you can go to 4, so you still have 2, 3, 4. And also, because you were in 6 before, you can now go to 7. So you can be in 7. Now, the next character comes is a C. If you're in 7, you read a C, you can go to 8. So now you can go to 8. If you go to 8, you can go to 9, and you can stay at 9. When you get the next D, now you're in 9. If you get a D, you can go to 10. But if you're in 10, you can take a free epsilon transition into 11, and therefore you have accepted this string. So the final problem is the back to the Boyer-Moore algorithm, where you are looking for some pattern in a text. We want to do this in an efficient way. Now, one of the things that Boyer-Moore does is that given the pattern, it can build the table corresponding to this pattern. In other words, that this is part of the pre-processing step, that you build a table to represent this pattern, so we can figure out where to jump when things fail. So for instance, this table always have the last occurrence of the character D in the pattern. So for example, pattern, you have 0, 1, 2, 3. So the last occurrence is 3. Same thing is 5, 0, 1, 2, 3, 4, 5. That's where the character is. That gives us a way to advance the string forward when you're searching for this needle. And same with L, that's going to be 4, the fourth character, and n is equal to 0. So we need this table to decide how to advance. Now let's simulate this on the given string. So we have needle. So the way the Boyes mover would work is that it compares the characters n and e, and it fails. This means that it needs to advance to the last occurrence of the n, which we know is 0. So therefore n is going to be a line here. So we'll have needle here. Now at this point, we compare x and e. Boyer-Moore, as you recall, go from right to left to save a lot of comparisons from doing a lot of comparisons. So because x is not in the table, in fact, we know because in this table will be made for the whole alphabet. If x is not there, then it'll be -1. So this means you are able to make the full jump to skip all the other characters. So suppose we have this situation now. In this case, we are matching E, matching L, matching D, and then finally we are trying to find we will be finding a mismatch here. D doesn't match with E. Now this is a tricky case. If you want to align this D with that D, we have to back up the string, and we don't do that in the Boyer-Moore. We always go forward. So in this case, heuristics don't work. So we advance by one character, needle. So we get this. Now, this point, we're going to be comparing A and E. And because A is not in the pattern, you are allowed to make a full advancement. So I'm going to start writing here. It'll be needle. And now we compare the following. We have an E matching, but this is not matching here. So what we need to do is to align with the last E, but again, this would take a situation where we have to back up. So instead of backing up, we're going to be going one forward, needle. And at this point, we compare D and E. They don't match, but D happens to be in the pattern. So the next step, we're going to align D with that D. So that's the first. So we'll have N, E, E. So at this point, as you can see, that this will match up with that, and we found the pattern. So if the question is what sequence of characters in the text with the last character, we know they are going to be N, and they're going to be X, and they're going to be E, they're going to be A, and they're going to be E again, and D, and E. So those are the characters compared. If you look at the things that we circled, there's only, in fact, we have to do all of these things to finalize things to make sure that we found the pattern. But the number of comparisons that you do can be very small if you're allowed to do the jumps. So this shows you that Boyer-Moore can be very efficient algorithm. And in fact, in the best case for Boyer-Moore is N over M, so which is good. But the worst case can be